Okay, so this is week 3 of our advanced essential oils training. And I know week 1 is up on YouTube. Week 2 is not on YouTube yet. I switched to a new computer, and so I don't think I put that on there yet, and I'll have to get that on there. But last week we were kind of going through, if you remember, we were going through the different extraction methods of essential oils. And we talked about the basic extraction methods that pretty much, all the ones that doTERRA uses. So we're going to start out today, with talking about some of the other extraction methods that exist, even though they may not be ones that doTERRA necessarily uses. So one of the extraction methods that saves a lot of money when you're making oils is going to do solvent extraction. So a lot of the ones you see out there are solvent extracted, and the reason why is because it saves money, right? It saves them a lot of money when they make it. So they put a solvent, they put that plant material in there, so they get all the plants and they put it in there, and then it'll make a concrete, and then that concrete and the alcohol and the heat combined, they put it through a condenser, and they come out with an absolute, which a lot of companies do using a solvent. Now what doTERRA does in this situation, because they do use solvents for a few, there's a few you cannot make without some kind of solvent, and that would be like jasmine, rose, I think even magnolia, floral oils like that, the fancy ones we know about. But what doTERRA does is they make sure that all of the solvent is then taken out of the oil. They don't have to do that. They could leave that solvent in, and a lot of companies do leave that solvent in because they don't care about the purity of the oils. doTERRA's philosophy kind of is that those are not really meant to be there. We have to use them to extract the oil because the petals are so fine, the oil is so fragile that they have to use something, but they don't want it to be in the finished product because it may affect the outcome of when we put it on us. It may have a different benefit or negative, even negative result because it has some solvent still in it. So doTERRA has, if you look on their page, also it tells you all about this process and how they come out with an oil that is free from all the solvents. Now, what typically happens in the industry is somebody who does this process will usually end up with about 1 to 6% of hexane in the final product. And hexane is not something, first of all, you can't consume it, obviously. It's not something I'd want for my body, and probably wouldn't want to inhale it either. It's pretty bad stuff. So some of the other extraction methods also were, besides the, let me go back to the solvents. So some of the other solvents that they might use might be the kind of like, you can use ethanol, you can use some kind of alcohols. These are different things that you can use to solvent extract, but it is something you still don't want in the final product. Now the final product is called an absolute. So our floral oils are really an absolute. So I want to make sure I am recording this, right? Yes, okay. So I just want to check, sorry. So when we look at our jasmine oil, for instance, that is actually a jasmine absolute, not an essential oil. So most of the essential oils are produced through steam distillation, or they may be cold press expression methods, but the jasmine, why can't I pronounce that today? My mouth is not working properly, it's the heat. But the jasmine absolute is produced by solvent extractions. And so they contain the aromatic and the non-aromatic compounds. And like I said, doTERRA works really hard to get those things out of there because they don't want us exposed to them. Another interesting method to extract oils, see there's so many different methods. I don't know if you've noticed how many we've gone through, but there are actually a lot, including what we went through last week. There's another called carbon dioxide or CO2 extraction. And some people have asked me about this in the past, and I know that we've talked about it in the past briefly, but it's not something we talk about a whole lot because we don't do it at doTERRA. Now, that is a process of using carbon dioxide, which is also called supercritical fluid extraction, SFE. And CO2 has the unique ability of reaching a supercritical state, meaning that it possesses the properties of both a gas and a liquid simultaneously at a relatively low temperature and at low pressures. That's useful to preserve the important volatile molecules, the ones we're looking for, right, that are more sensitive to heat. So before we go into the science of the process, here's why it's cool. It's really clean. It doesn't leave solvent residue in the essential oil, and it protects the chemical structure of the volatile compounds, preventing them from changing during the extraction process. and no more turning linyl acetate into linalool. And that's a very important thing because linyl acetate is going to act different than linalool. And one of the problems is in certain extraction methods that people use, distillation processes, they might accidentally, through too much heat or whatever, turn that linyl acetate into linalool. And that is not something we want to do, right? So we have better control of extracting the aromatic compounds, so you can get heavier molecules that otherwise might be left out, like the diterpenes in frankincense. We're going to talk about diterpenes later because they're actually quite rare in essential oils. It also produces a highly concentrated essential oil that smells like the original plant material. So the way it works is you get clean, more complex essential oils that are closer to the plant's natural composition. And equipment for this type of extraction is expensive, but the overall process is pretty fast and efficient, and it often produces higher yields than even steam distillation. So the way it works is the CO2 is heated and pressurized, which turns it into an excellent solvent. Next, you put the liquid CO2 in with the plant material, and this pulls out the essential oils. You can get rid of the now oilless plant material, and once that plant material is filtered out of the mixture, the heat and the pressure are turned off. Now, when that happens, the CO2 turns back into a gas and evaporates out of the oil, right? And it's captured to use in the next batch. And the result is the pure essence of the plant in a bottle. So another one we will also talk about today is Enthrage. Sounds pretty, doesn't it? So this is an extraction technique that is one of the oldest methods known, and it was used to extract aromatic compounds before distillation was even invented. So we can imagine like Cleopatra's perfumer extracting rose oil for her to use, and this is how he did it. He uses lard. Okay, well, that's a little simplistic. There's some interesting science behind it. Enthrage really highlights the lipid-soluble nature of these volatile aromatic compounds. And so you remember that if something is lipid-soluble, that means it dissolves in fats, right? And with Enthrage, the plant material is crushed, it's pressed into an animal or a vegetable fat. The lipid-soluble compounds, that's to say the essential oil of the plant, dissolve into the fat. And after you've pressurized the plant materials, you're left with a greasy, waxy mixture called an Enthrage pomade. That sounds nice, right? The pomade is then further processed with a solvent, like hexane, to separate the fat from the essential oil. And the finishing touch is washing the product a second time, typically with alcohol. And in the end, you're left with an absolute, but not a really clean one. So Enthrage produces impure products. It's not considered an acceptable method for producing therapeutic grade botanical extracts, which is why doTERRA doesn't use it. And while it's historically important, there are so many ways of extracting essential oils that are a lot more efficient nowadays. So it's really not that relevant today. Plant material laid into the fat alcohol fragrant oils absolute wooden frame is called our Enthrage here. You can see this is what that is. That's a wooden frame that they used to use. It's not something we use. So which extraction method is the best? Well, it really depends on what you're looking for, right? If you're trying to obtain essential oils for fragrance purposes, like perfume, right, then absolutes, expression, and CO2 essential oils produce the most authentic aromas. So that's when you just want it for just the smell and just for the sensation of the smell, not for the benefits we get when it activates our olfactory nerves, right? So when it comes to therapeutic grade oils, having the optimal ratio of key volatile molecules is really what matters. So to determine the best method for producing the right ratio of aromatic compounds, you can compare different types of extraction on the same batch of plant material, right? You probably don't have time to do this, so we took a batch of roses and we did it for you. Another big thing to consider is pesticides. If the plant matter was sprayed with pesticides, so I get a lot of questions about this, you know, I'm sure you guys do too, about pesticides. So if the plant matter was sprayed with pesticides, the solvents tend to carry and concentrate those pesticides into the end product, which is not a good thing. If you're using a solvent extraction method, including CO2, you have to make sure the plant matter is free of pesticides. In the end, qualified scientists and health professionals need to carefully evaluate and compare the various extraction methods for each plant to determine the preferred extraction method. So going the extra mile to do this maximizes the efficacy of the essential oils produced, so you can expect consistent and reliable results. So let's see who's here. I'm going to test you now. It's Jessica, so you're going to have to answer this for me. Okay, so why don't we like to use, and why doesn't doTERRA use CO2, Enthrage, and other extraction methods like this?
I'm looking at the Enthrage page right now, but it's because they want to get the purest form of oil possible.
Right. They don't want to have
Yep.
contaminants in it. They certainly don't want any of the solvents in there. And so they use methods that get those out, that will make sure those things are not in the finished product. So then we ask about, how do these oils affect us? So now that we have kind of a better understanding of what they are and the basics of how we extract them, we're going to move on to kind of the chemistry. So this is going to be either very interesting or very boring, depending who you are, I guess, right? And once you understand the chemistry, then you'll be able to use them more safely and effectively. And chemistry really helps us. If we can understand the chemistry more, then we can help ourselves more even. So if we know that we want to have a certain result and we're looking for it, like let's say I know that I want to have the results that I can get with beta-carotene. Well, if I know which oils contain that chemical compound, and that's what I'm looking for, the benefits of that, then I can go to those oils to solve a specific issue, right? And so when we look about what chemistry really is, okay, so everything around us, from the air we breathe to the clothes that we wear, is made up of different substances. And substances consist of these tiny particles called atoms, we've all heard of that, which are made up of even tinier particles called electrons, protons, and neutrons. So everybody remembers this back from, what, junior high science, right? And chemistry studies substances at this tiny atomic level. So there are a lot of different types of atoms, and how many electrons, protons, and neutrons an atom has determines what element it is. So you've probably heard of elements such as oxygen, hydrogen, and helium, right? Everybody's heard of those. O, H, for helium. The atoms make up these elements. Will have different numbers of protons, neutrons, and electrons. And altogether, there's 118 different elements, and they all have unique combinations of protons, neutrons, and electrons. So then what's a molecule? Okay, so when two or more atoms link together, it creates a molecule. So water, for example, is a molecule. And you've heard it referred to as H2O because it has two hydrogen atoms and one oxygen atom that are linked together. And this molecule is what you drink to stay hydrated every day. So when it comes to essential oils, we focus on organic chemistry. Now, organic chemistry is the study of the molecules that have carbon in them. So if a molecule has carbon, it's considered an organic molecule. Carbon gets a lot of attention because it's so good at building molecules. It loves bonding with other atoms, and it's stable enough to make the complicated molecules that are necessary to create life. So without carbon, you can't have DNA, and then we wouldn't be here, right? So an important feature of carbon is its ability to make large or complex chains. Now, these chains of carbon atoms are referred to as a carbon backbone. So other atoms will build on this backbone to create the whole world of carbon-based molecules. So we'll talk more about carbons in a bit, but right now we're looking at carbon-based molecules. So remember how we talked about the chemical compound linalool in lavender essential oil? So here is a basic diagram of what makes up linalool. Oh, I lost part of it when I put that little fancy thing there. Let me see if I can find it. Oh, shoot. I lost part of it. I shouldn't have done that. It didn't show me that. Okay, so I apologize. I've left out part of it, but this is most of the molecule of linalool. In the graphic, you see letters like C, H, O, and these letters represent the different atoms in a linalool molecule. And in this example, C stands for carbon, H for hydrogen, O for oxygen. So one of our more simple ones, right? All the simple things. And another thing that you need to be aware of is the number of chemical bonds between atoms. So this molecule has both single and double bonds, which are represented in the diagram by one or two lines joining the atoms. You don't have to worry about it too much, but just wanted you to have some background. So you see some of these where there's two lines for a double bond, and then you've got single lines for a single bond. You see all the carbon, the hydrogen, all different, right? So molecules matter. The different molecules that are found in essential oils are what give them their therapeutic value and the aroma. It's really hard to believe that it just kind of comes down to these little dots, really, right? Just looking on a page, or these little letters on a page, is very strange. But the chemical makeup of the essential oil affects how the oil interacts with your body. So each essential oil has a different number of molecules. So for example, wintergreen is almost entirely made up of one kind of molecule called methyl salicylate. Spikenard, on the other hand, has hundreds of different molecules. And few people really appreciate the complexity of essential oils, particularly the oils that contain hundreds of molecules. Too much or too little of any given molecule, so one little tiny piece of that oil, can affect the aroma and the properties of the essential oil. So we kind of looked at the chemistry, the importance of the molecules in the oil, so we'll go one step further. So remember we talked about how molecules are atoms that are linked together through a chemical bond. Well, if the atoms that are connected are different types of atoms, they're not only a molecule, but also a compound. So because water has both hydrogen and oxygen, it's both a compound and a molecule. Ozone, which is just 3 oxygen atoms joined together, is only a molecule. There's no compound because it only has the one type, which is the oxygen atoms. And essential oils are filled with all different kinds of compounds. And what these compounds have in common is that they're volatile. So we talked about it before, but in case you need to remember, volatile is why when we open our bottle, every time you open a bottle, some of it is going to convert to a gas really quickly. Now, part of that's good. It's converting to a gas, which means it's escaping the bottle. It's coming up into my nose and, oh, I'm smelling it, right? Because the gas is coming out. On the other hand, if I leave it open, I leave it on my counter, this is going to keep escaping and eventually my bottle's going to be nothing, right? That's why we keep them covered and we keep them in cool, dark places. So now that you kind of know what the molecules and compounds are, and you understand kind of the importance of the carbon in building compounds, it's time to really dive into the chemical structure of essential oils. So one of the things that's really interesting is that no 2 plants will produce essential oils with the exact same chemistry. Even 2 plants from the same species will have variations in their chemical composition. So there's a lot of things that affect it. Obviously, the region it's grown in, the time, the season it was harvested, the quality of the soil. And so this means that like lavender grown in Bulgaria actually has a different chemical composition than lavender grown in the Himalayas. So the main difference between the 2 plants is usually the amount or percentage of the major compounds for that species. So lavender from the Himalayas and lavender from Bulgaria will both have the compounds linalool and linyl acetate, which we know and love so much, right? Have some great benefits, but they have differing amounts. And as we talked about earlier, the amount of any given chemical constituent in an oil affects the benefits of that oil. So when we look at this, this is very interesting because you look at ours, which is Bulgarian lavender. That's where we mostly get the lavender essential oil from. You can see it's got a little bit less of the linyl acetate, slightly more of the linalool, but then it's got totally different ingredients here. And when you look at things, like if you're looking at Himalayan lavender, you see it's got beta-caryophyllene at 3.8%, not bad, right? And the caryophyllene or beta-caryophyllene is a natural bicyclic sesquiterpene that is a constituent of many essential oils itself. And it's especially like clove oil or oil from, let's see, from cannabis, from rosemary, from black pepper, melissa, copaiba, and hops even. So that's where you're going to find something like beta-caryophyllene. So if you're getting your lavender oil from Bulgaria, which is where doTERRA comes from, then, and if you're looking for it for its benefits with the beta-caryophyllene, for more of the benefits you're going to get from that particular chemical, right? Then you're not going to want that oil, or you're going to pick up one of the other oils that is high in the beta-caryophyllene to make up for it. And that's why sometimes you mix lavender with something else that maybe has some of these other ingredients, and you're going to get a completely different result because you've actually created a different chemical makeup, right? So when we're blending oils, we are actually creating a whole different reaction, really, because of the way that they're bonding together and the different constituent parts that are in there. So sometimes the environment can impact a plant so much that it produces a totally different chemical composition. So 2 plants can have the same genus and species and diverge within the species into different subspecies, which scientists will call chemotypes. And even though 2 plants look and grow the same, inside their chemistry is so different that they're categorized as a different chemotype. And the chemotype of an essential oil is important because it can influence its effectiveness and safety. So what causes plants to have different chemotypes? Well, the chemical constituents of the plant are different because of minor changes in the makeup of their DNA and how the plant's genes are expressed. So think of identical twins, right? Same DNA, but slightly different appearances. Have you ever met identical twins? Have you ever meet them? And you see that they're different, right? And this comparison of 2 chemotypes of basil will show how different their chemistry can be. So this is very interesting when you look at the country of origin, you look at its chemotype and its major constituent parts. These are very different when you look at this, right? Look at that. A lot of these ingredients, the linalool, they've got the chavicol, so this is very little of that. What a big difference. They're going to act completely different. So now when we talk about also the chemistry of essential oils, we're going to start with something called terpenes. Okay, so I'm going to go over a few of these, and I'll kind of watch the time, and when we get tired of doing this, we'll just stop, because I don't want to overburden you today. We're going to start out with terpenes. So when we talk about the chemistry of essential oils, we have the terpenes, and that's a type of aromatic molecule that's created by plants. This is called terpenes. So why are they important? Well, out of the 3 different types of terpenes that are related to essential oils, monoterpenes, sesquiterpenes, and diterpenes, monoterpenes and sesquiterpenes are the main compounds that are present in essential oils. And they are basically the building blocks of essential oils. Diterpenes aren't frequently found in essential oils because they're heavier and don't easily evaporate during steam distillation, but like we discussed earlier, there's a little bit in frankincense, right? So I'm going to go back to this previous slide about basil, so we can do some comparisons. So when we're looking at the different types of basil and where they come from, you can see that they are very, very different. So when you look at that, do you notice the differences? Can you see the differences immediately right off the top of your head as you look at them? You see that these are completely different, right?
Oh,
so the
yeah.
Phenols there. I mean, they have the basic, Lineal, the chavicol, right? That's there. Even they got the 4 same ingredients, but totally different amounts, which means it is going to act totally different. So let's go back to monoterpenes. So let's look at some of these monoterpenes. So monoterpenes have a 10 carbon atom backbone that are arranged in either a ring or a straight chain. I know that means nothing to us, right? And they're found in virtually all essential oils. So the monoterpenes come in different types of shapes. They can be circular, straight, or branched. They're also clear, fluid, and aromatic. So each possesses its own unique function. So they're really small, which means they react quickly to air and heat. Their small size also allows them to absorb very easily into tissue, fit through the small spaces of cell membranes, like we discussed earlier. And so remember that monoterpenes have an easier time getting inside of our cells. So limonene and linalool are 2 of our very common monoterpene molecules that are present in many essential oils. Citrus oils have really high amounts of limonene, and lavender, clary sage, basil, cilantro, and coriander have high amounts of linalool. And you can see on this chart here, you can kind of look at them. What do you see here? You see a lot of our fruit oils, right? You see all that limonene that's in them? Some of the key components there. These are some of the monoterpenes. And now we have some of our sesquiterpenes. So our sesquiterpenes are heavier than the monoterpenes, and they have a backbone of 15 carbon atoms. Their larger size makes them less volatile, which means that they don't evaporate as quickly. So you'll see that these oils, they're not going to be the ones that kind of just disappear out of the bottle over time, right? Because they're less volatile. This also makes it a little bit more difficult for them to cross into our cells, but they're still below the molecular weight that allows them to do so. So their superpower is their unique shapes, which allows them to adhere to proteins and activate receptors on the surface of cells. The fact that sesquiterpenes can interact with proteins is significant because proteins are really what facilitate everything that happens in a cell. And since the cells are the building blocks of our body, then the sesquiterpenes affect proteins, which run the show in your cells, which therefore impacts the health of your whole entire body. An essential oil can have both monoterpenes and sesquiterpenes, giving it a broad range of benefits. For example, frankincense has both monoterpenes and sesquiterpenes, which allows it to interact with cells in a variety of ways inside and out. That's why we find that frankincense is so versatile and does so many different things, because it has a lot of these the base chemicals in them, right? So here again are some of the ones that we see with sesquiterpenes in them. They're broke down. This is the linalool, a better drawing there of the linalool, so you can see the hydrogen, the carbon, the oxygen on those. Now let's see. In addition to the terpenes, essential oils also have a molecular group called the chemical family. So the chemical families, so this is something different. This is chemical families. And those are alcohols, aldehydes, alkynes, and so forth. More of them in a minute. And the compounds that make up the essential oils can be both a monoterpene and an alcohol at the same time, or a sesquiterpene alkene, or a monoterpene aldehyde, and so on. Think of it like sticking a chemical family building block on a terpene building block to make something new. So every possible combination of terpene and chemical family represents its own unique class of molecules. And there are 9 main chemical families in essential oils, so we're going to talk about each of them briefly. So we've got the alcohol family. So this is the alcohol family here. It's a molecule with a specific arrangement of atoms, an oxygen atom bound to the carbon backbone on one end and hydrogen atom on the other end. And there are multiple alcohols, but they all share the same group of atoms. So it might be easiest to kind of imagine alcohol molecules as like being a certain shape, let's say a triangle. And you can have different angles, but it always has the same basic structure. And anytime you see it, it's recognizable as a triangle, right? And each chemical family has its own basic shape made up of a unique group of atoms. But back to alcohols. In general, alcohols have names that may start with the parent terpene they were derived from and end in OL. Examples include menthol, geraniol, linalool, cedrol, cusamol, terpenine 4-ol, and citronellol, right? So what do alcohols do for an essential oil? Well, keeping in mind, you can have monoterpene alcohols and sesquiterpene alcohols. So what do they do for an oil? Well, essential oils with alcohols are known to serve as powerful cleansing agents. They provide antioxidants, support restful sleep, support a healthy cardiovascular system, provide a really uplifting aroma. And not all alcohols have these exact properties, but these are commonly found in various alcohols. So this principle is true for the other chemical families that we're going to discuss. So which essential oils contain alcohols? Well, those would be oils that are high in monoterpene alcohols like tea tree, geranium, coriander, basil, jasmine, and lavender. And essential oils that are high in sesquiterpene alcohols include sandalwood, vetiver, cedarwood, and patchouli. So then we have our phenol family. So our phenol family, also referred to as phenolics, are a special subtype of alcohols. They're made up of an alcohol group, which we talked about earlier, made up the oxygen and hydrogen attached to a benzene ring. And this is some of our phenol and what our phenols do. You see they're a repellent, they're antioxidant. And one thing I did notice when I was looking at this too, oregano, clove, thyme, what do we also know about these?
Yeah, you can cook with them.
That's true. That's another thing. But these are all hot oils. Yep. These are the ones we do not put in our mouth directly ever, right? That's what we remember about that. If you've ever done it, you'll definitely remember it. Okay, so then we're going to talk a little bit about geraniol. Whoops, where did my thing go there? Okay, so did I not? I think it is here. Okay. Now, benzene ring is made up of 6 carbon atoms arranged in a hexagon pattern with exactly 3 double bonds inside the ring. We probably don't care that much about that part, right? But phenols are quite potent, and because of this, essential oils that contain phenols may cause skin irritation. Like alcohols, their names end in OL, and so common phenols, which I think you've heard us talk about before, are things like carvacrol, eugenol, and thymol. And you can have monoterpene phenols and sesquiterpene phenols, but sesquiterpene phenols aren't commonly found in essential oils. So what do phenols do for an essential oil? Well, essential oils that have phenols, are known to offer antioxidants, repel insects, aid immune function, and to be very cleansing. So essential oils that are high in monoterpene phenols include, of course, thyme, oregano, clove, some of the other ones, cinnamon bark, cinnamon leaf, and basil. I wonder if basil would, is that a hot oil? I don't use that one, I don't know.
I'm not sure.
I'm not gonna put it in my mouth to find out though, so somebody's gonna have to tell me. I'm not doing that again, that was a mistake. Okay, and then we have the, I don't know where I got to menthone, I think I skipped ahead. Yes, the aldehyde family. Okay, I skipped one. Oh, I skipped this one. Okay, yeah, we want to talk about the aldehyde family. So again, we're not really that interested in the chemical structure. What we want to know is what do they do? Well, these aldehydes are unstable. They're susceptible to oxidation when they're exposed to oxygen and low heat, making it really important for them to be stored properly. And oxidized oils will actually irritate the skin far more than non-oxidized oils. And this is something we haven't discussed before, I don't think, and something I didn't know before, but sometimes you'll get somebody and they'll say that it irritated their skin. And we're always thinking, well, maybe you're just sensitive to that oil. Well, actually, it might just be that it's oxidized. And this is, again, why when people ask, you know, could I just buy my oil on Amazon? I'm like, you don't know how long it's been there, guys, you know, and you don't know what it has been treated. you do not want to buy your oils. That's why we want people to have their own accounts, because we want them to get them directly from doTERRA, bring them into their homes and store them properly, because that way they're going to have the best effects. These are medicinal grade. We do not want people using them incorrectly. We don't want people having reactions to them or sensitivities because they've been oxidized or they've been mistreated, right? So this is really important, especially when we're looking at some of the oils, which can be oxidized very, very quickly. And it also can change the aroma and even the therapeutic benefits of an oil. So, and this is something interesting, and this actually happened to me. I have 2 grapefruit oils, and they're 2 different colors, and I was wondering why. And one of them is about 2 years old, and I got it when they had the specials in Europe at Christmas. So somebody had brought it to me, and I don't know how it was treated. And then I have the other one that I got here directly, and it's pretty new. And they smell completely different to me. They're a different color than each other as well, but they smell different to me because one of them has oxidized, probably would make sense, because those are oils that oxidize very easily. So I have to be really careful with that, right? Make sure they're treated properly, make sure they stay out of the sun. So, if they're known for their distinct, potent fragrances, that's what essential oils are known for. And the aldehydes can be a key contributor to the overall aroma of that essential oil. But again, if it's oxidized, that's going to have a different smell, right? And aldehydes will usually end in AL or aldehyde. So the common ones we see in our essential oils are cinnamaldehyde. Guess where that is? Geraniol, is nerol, decanol, and cumanol. So you can have monoterpene aldehydes and sesquiterpene aldehydes, but sesquiterpene aldehydes aren't commonly found in essential oils. So you look at some of these: cassia, lemongrass, cinnamon. It tells you what's in them, like geraniol, which is also in geranium, and nerol, which is also in, I think is it neroli? I think it's neroli. And then of course, cinnamaldehyde is also, in both cinnamon and cassia. And you see why cinnamon and cassia smell so different, because I don't know if you've done it. I've done it because I love the cinnamon. The cinnamon bark oil, I think, is the best thing in the world, and it goes in my tea every morning. But I thought I could save money because that cassia is a lot less expensive. So I bought cassia and I smelled that and I actually stuck it in my tea. Oh, gross. It does not taste the same. It is completely different. So just because it has some of the same benefits doesn't mean, this benzaldehyde apparently totally ruined it. That's what I figured anyway, right? So the aldehydes are good because they have lots of great health benefits, including obviously the antioxidants. They're very, very high in antioxidants. Really good for healthy digestion, for gastrointestinal function. The ones, of course, that are high in the monoterpene aldehydes are cassia, cinnamon, lemongrass, as shown here. Melissa and cilantro are 2 others. So also similar to that, aldehydes are the ketones. So the ketone family of molecules. So the ketones are molecules with, we don't need to know this stuff, the carbon atoms, blah, blah, right? Boring. Okay, most ketones end in one, O-N-E. Examples of ketones will include things like camphor, carvone, diavinone, jetamansone, leptospermone, menthone, mustacone, and rotundone. Who names these things? They are really hard to say. So what do the ketones do for an essential oil? Well, the essential oils with ketone molecules may improve the appearance of the skin, support healthy respiratory function, and promote healthy digestion. And the oils high in monoterpene ketones, so we're going back to it's a monoterpene and a ketone, right? Includes things like spearmint, dill, peppermint, geranium, caraway. That's one we got free. Is it this month? This month, yeah, we got our free ones this month. And spikenard is an oil that's high in sesquiterpene ketones, which isn't as common. So it's just, we mentioned the spikenard oil for that. And then we have the alkane family. So the simplest organic molecules, alkanes, consist entirely of single bonded carbon and hydrogen atoms. So it's a very simple, did I skip one again? I'm trying to, I don't think I had one for these. I couldn't find one, nope. Okay, so we'll just talk about it here. For essential oils that contain alkanes and those that do typically contain really small quantities, examples of the alkanes are nonadecane, henecosane, heptadecane, tricosane, icosane, nonane, undecane, pentadecane, and pentacosane. So the reason I tell these to you is because it's just funny trying to pronounce the names. So I hope you're enjoying that with me. Luckily, we don't have to usually say those names. We just tell what the oils do, which is obviously a lot easier to pronounce. But I thought I'd throw those out there just for fun. Okay, so what do oils that have alkanes, what are they known to do? Well, they're known to soothe the skin, promote relaxation, to be balancing, and to be grounding. So I don't want to talk about the chemical bonds of it because it's kind of boring. They are excellent receivers of unpaired electrons in free radicals. And so that's helpful because we don't want free radicals or unstable atoms running around our body, right? So, you know, we don't want them bouncing around in our cells. We don't want them causing problems and breaking things. And so we can use something from the alkane family to receive those unpaired electrons so that we don't have them running around loose in our bodies. I always wanted to see, like, it would be so cool to make a little video to show what kind of is happening inside our bodies when you have like loose free radicals and what they're doing. I envision them as like those army men. They're just running around and being problematic. And then I'm using the oils to knock them down.
Yeah.
Okay, so alkene molecules usually end with an ene, such as alpha-pinene. That's what we hear it all the time. Beta-pinene. We also hear limonene, saponine, gamma-terpenine, germacrine, D, beta-carotene. We hear about a lot. Zingiberine. I don't know where I've heard that before. And alpha-cedrine. So they can rejuvenate your skin, promote an uplifting environment, provide those antioxidants, support healthy inflammatory responses. That's a good one. And some of them are mentioned here, and you can see them on the no, not on the screen because I'm not on that screen yet. Oh, I don't have a screen for that, right? Okay, so the ones that are high in monoterpene alkenes are going to be your frankincense, Douglas fir, blue tansy, green mandarin, lemon, lime, pink pepper, red mandarin, tangerine, and wild orange. So what I noticed about that is about half those oils are ones that I previously really didn't know what to do with. I don't know about you guys, but we got a lot of times those free things, right? I bought a blue tansy because I wanted to have a cool blue oil. Don't know really what it does. But green mandarin we've gotten for free. We got pink pepper for free, and the special we got red mandarin for free. You know, so we've been getting some of these, and we've been wondering, gee, what do we do with them? Other oils that are high in sesquiterpene alkenes, so this is opposed to monoterpene alkenes, right? And the sesquiterpene alkenes would include the ylang-ylang, black pepper, copaiba, melissa, and ginger. Now, I don't know if you notice what I notice, but when I look at the different oils and they're associated with things, they don't remind me of each other. It's like they have a lot of the same chemicals in them, but they don't act at all the same because of the other things that are in them. So you notice that you're not seeing, like, I'm not saying things together like lavender, copaiba, and the ones we find relaxing, right? I'm not saying all those together because that's not how it works. It's the balance of the different oils, the different chemical molecules in them that predict how they will perform in the body. So now we can talk about the esters. So the ester family is a chemical family that is really the reaction between an alcohol and a carboxylic acid, and that's called esterification. And esters have a central carbon atom that's bonded to a single, oxygen atom, to the carbon backbone, blah, 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 right? Boring. Okay, so they are oxygenated compounds, which means they have oxygen as part of their chemical structure. So they usually contain 2 carbon chains, and they have 2-word names with the second word ending in -ate. So some of them are, so I'm going to test you here. What is one of our most common constituent chemicals that ends in -ate? ATE.
I would say acetate.
Yep, linylyl acetate, the one we always associate with lavender, right? Then we have bornyl acetate, methylamyl angelate, methylthujate, methyl salicylate, and neryl acetate. And you can have monoterpene esters and sesquiterpene esters, but sesquiterpene esters aren't commonly found in essential oils. So you notice that the sesquiterpenes that we've been mentioning, most of the sesquiterpenes are not found in the essential oils with one of the family groups. So what do the esters do for an essential oil? Well, essential oils that contain esters they're usually calming, they're relaxing and balancing. They reduce skin blemishes, they're soothing when applied topically, And the ones that are high in those monoterpene esters include things like lavender, clary sage, bergamot, jasmine, Roman chamomile, helichrysum, arbor vitae, and wintergreen. And again, you don't find cis-terpene esters not usually in essential oils. We'd have to ask nature why. I wonder why. I'm always curious why that happens. So, oops. Is it the one on the last one on slide? Okay, so here, I'm going to go back and talk to you real quickly here. Okay, so this is me again. So we do have another family called ethers. I apparently don't have a screen for this, so I'm just going to talk to you about them. Now, they usually end in ol, like 1,8-cineol, or also called eucalyptol, and things like anisole, crizarine, furanudesma 1,3-diene. Okay, that is really hard to say. Who names these things? I have no idea. They really got to make this easier. But essential oils with the ether molecules in them really help promote feelings of clean airways, improve the appearance of the skin, provide cleansing benefits, and support proper immune function. And oils that are high in monoterpene ethers include things like cardamom, eucalyptus, rosemary, tea tree, and peppermint. And the oils high in sesquiterpene ethers, so this is where you see the sesquiterpenes with something else, right? Sesquiterpene ethers are going to be myrrh and vetiver. What else is very common that we know about myrrh and vetiver? What is the most similar thing about them? Do you know?
I'm not sure.
Okay.
I would say my first response would be like a calming or grounding or effect.
Okay, it's actually more simple than that. If you've used both of them, those are the two oils that take forever to come out of their bottles.
Oh, yes, yes.
They're very thick oils.
They're very thick.
Yes, yep, that is true. So I kind of want to stop here because I don't want to overburden. I want to have a chance to kind of discuss this a little bit. So one of the things that, you know, as you're looking through the chemicals, the various chemicals that are in the oils, and you think about, you know, why do they seem so different? Because they do seem different. And in fact, some of the ones that seem similar actually have a substantial difference in their chemical makeup. So if you look at some of the ones, what are some of the ones that are familiar? Can't think off the top of my head. Okay, so anyway, you know, the reason we want to know the chemical kind of makeup of the oils is because when we're trying to combine oils, like let's say you do some reading, some research, and you say, hey, you know what, I have this condition and it says it responds really well to thymol. Okay, where is thymol located primarily? Do you know this?
No.
Think about it. It's not a trick question. Where do you think thymol would be the most?
I don't know.
You don't know? Okay, I'll tell you. Thymol is in thyme.
Okay. Come
Was
on.
it too easy? I told you this wasn't a trick. Yep, thymol is in thyme oil. So what you do is you want to know what's in some of the other oils, because let's say you have another oil and you're trying to solve a specific problem, and thymol is one of the things you want to use, but you don't want to use too much of it. And you don't want to combine thymol, let's say, with another oil that's really high in thyme, with another oil that's really high in thymol. So what we do is, us as kind of like, we're not experts in this field, certainly, right? What we do is we get out like our Modern Essentials book where we can look up the chemical constituent parts of the oils. And that's one of my favorite things about the Modern Essentials, is because it will tell me for each essential oil what its chemical makeup is. So I can make sure I'm not getting too much, or that I'm getting what I want. So again, we go back to when we were looking before about lavender. So our lavender, which comes from Bulgaria, does not have the beta-caryophyllene in it. But if we're looking for beta-caryophyllene because that is solving a specific problem, we're going to want to combine lavender with another oil that is high in that. So for me, I would say something like copaiba. So if I'm trying to get that effect and I want the same effect of beta-caryophyllene, I'm going to go get it in my copaiba, and I'm going to mix copaiba and lavender, which is why, you know, how we're talking sometimes, we'll say, you know, if you put lavender with this oil, it works so much better. That's what's happening.
Okay.
You're getting more benefits because you're adding another oil, and then they're having a synergistic effect, and they're having a stronger effect on the human body. So especially if you're using, let's say you're using lavender for an antihistamine, you're probably going to want to combine it with something else to get the full antihistamine effect of whatever the issue is, right? But that means you have to understand the chemistry a little bit. And the chemistry part is hard. First of all, we can't pronounce half the words, right? So that's the hardest part. It's just pronouncing the words.
Right.
So we can't pronounce the words. So what we want to do is, I'm doing this advanced training. You know, doTERRA did this an advanced training. I'm following up with this and kind of summarizing it and discussing it, because where I want to go with this is towards the end of our training, what I want to do is start discussing the different chemical makeup of the different oils and how we start combining oils if we're trying to do that. So if we're combining an oil for a problem, and we're going to actually walk through, so this is something to be done in a few weeks, right? We're going to go, we'll be on here and we're going to go through, you know, I've got a problem, let me solve it. And now what am I looking for? And we're going to do that on a chemical level with the information we have on the chemical makeup of the essential oils that we're using. And this is why a lot of times when you get an oil from a different company, it may act completely different. So sometimes you get an oil and you'll try another oil from a different company and you'll be like, yeah, but that one's not working. It may have a completely different chemical makeup. Just because it's lavender doesn't mean it's going to be highest in the lineal acetate and linalool that we're looking for. As we saw with the other lavender, it could be lower in some of those things. And if that's what you're looking for, then that other one's not going to work the same way as the one you were using, right? And I've had that where people call me up and they'll say something like, yeah, I went to the store, I got stung by a bee, I went to the store and I got the Now brand of lavender oil, I put it on and it didn't work. And I was like, yeah, I haven't tried it on a bee sting because I know better. I get my, I get the lavender essential oil that I have, which is from doTERRA, and it works every time, right? It gets rid of that stinging sensation. So all I can guess is that whatever lavender they got is not designed for that purpose. And that's why we learn what doTERRA essential oils are designed for, because they have a different chemical makeup than the same oil might have from some other company. And that's a really important distinction when you're trying to solve a problem, right? So everything we learn that is very specific to doTERRA. And that's why, because you saw the big differences, that's why it's very specific to doTERRA.
Nice.
Okay, so I'm going to finish up there. And then next week we'll dabble just a little bit more into the chemical, and then we'll finish that off. We'll ask some, we're going to do some combining, figuring out how we would combine solving some actual problems. You put this, so we're going to take what we learned so far and kind of put it into action, because what we've learned right now is very abstract. And I'm sure you're confused, a lot of people are after this point, because it is abstract. It's all these weird chemical names, carbon molecules, bonds, chains, whatever. That's all you're hearing, right? I mean, because that's pretty much what I'm getting out of it, is I'm just hearing all these chemical names. Yeah, they sound cool and everything like that. But now we want to figure out exactly what do these things do for us? What can we tell our customers when we're telling them? So one thing I want you to take away from today is really, hey, you know what? When you use an oil from a different company, you're going to get a different result, because they are different. They came from different areas of the world. They were picked at different times. They had different weather, whatever. It's going to be different. And different isn't necessarily bad, but it might be, especially if you've been trained to use one specific type. We spend our lives being trained in doTERRA, so we understand what they're for. We know that doTERRA's worked really hard to grow these in places that solve specific problems. doTERRA wants their lavender essential oil to be something we can use as a natural antihistamine, as something to help with itching. If we have itching, if bug bites and bee stings, they want it for that. That's what we use it for. We want it for its calming, right? We want it to help us sleep at night. So that's why we want the lavender essential oil, and other companies may not have that same benefit that we're experiencing with doTERRA. So I see you guys in next week for another advanced education, and bring any questions, okay?